Welcome back to ECE 320A. Your passport assignment is due on Sunday. That is helpful for me to learn names and faces, and in this class, what is it, a hobby, I think, that I'm asking for. You're supposed to be reading and studying Chapter 10, which is sinusoidal steady state material. Homework number 1 is due in a couple of weeks on the 29th. That's, I think, a Tuesday. And you have to access that homework assignment through D2L. And that D2L link should be on the home page of ECE 320, just to get you thinking about what is coming in the future. Exam number 1 is scheduled for Valentine's Day on the 14th of February. Don't you love it? Anyway, exams are just during regular class times. We'll meet here just like a normal class, and you will have 75 minutes for the exam. Question?
The first exam, what chapter does that go into?
The question is, what material will be on exam number 1? I don't know. I think it's whatever homework assignments are assigned before exam number 1, it's probably homework 1 and 2, maybe homework 3, but it's going to be chapter 10 for sure, and probably part of chapter 11, which is three-phase power. I'm not thinking we'll get Laplace there, but there's also a practice exam, I think. If I opened that up yet on D2L, there should be an exam 1 module, and you can look at those practice exams and see what content is covered and the exam topics in that exam number 1 module inside D2L. That's a better answer than what I'm giving you. So look at that, and hopefully that will prepare you for what material you are going to be held responsible for exam number 1. Today what we want to do is start chapter 10, which is single-phase power. That's the 1-phi. We will get into three-phase power, which is 3-phi. We have 3 different phases, an A phase, a B phase, and a C phase, and we'll have different phase sequences, positive phase sequence, negative phase sequence, etc. Right now we want to get or become experts with single-phase power, and that transitions us then into three-phase power, which is chapter 11. We'll start after we talk a little bit about power. We'll talk about a single element, a generic element, instantaneous power. That's just VI. And that will be a function of time. But typically we don't want to see all of that information. We're just interested in averages. And we'll talk about the average power. This particular formula is for real power. That's how much power is actually used to, let's say, go or convert between electrical and mechanical, etc. There's something we will learn, and that's why power is then in quotes in the next item. We'll learn about a power that is orthogonal to real power, and it's reactive power. And C's and L's, capacitors and inductors, have reactive power. And if we combine these, we'll have some generic impedance, and then we won't necessarily have everything in one orthogonal direction. We'll have some combination, vector sum of the real power and the imaginary power, or the reactive power, to give us the complex power. And the complex power, if you compute it, you can find it by taking the voltage phasor and multiplying that by the complex conjugate of the current phasor of that particular element or subsystem, etc. That's where we're headed. So to begin, let's establish convention. This is chapter 10. Here is a generic element, and we'll be talking about absorbed power and delivered power, but we will be using the passive sign convention. And the passive sign convention really just means that the current that we've defined, And we can define that current however we want, but in this picture, let's say that I've defined positive current to be flowing from left to right into that generic element, and I've labeled the voltage terminals positive and negative as depicted from top to bottom. Passive sign convention says that this generic element will absorb positive power, and whatever happens, if I now get a negative absorbed power, then that particular element is generating power. But the absorbed power is what I'm computing here, and then I just have to figure out what is my sign. If it ends up being positive, then it's truly absorbed. But if I end up with a P, a power value that's negative, then it's actually delivering. But that's the passive sign convention, and you have access to all of these notes, so I may not spend a lot of time for you to write that down, and I will scroll through. I'll slow down when we start going through some of the details or some of the calculations. I do think there's something to be gained from you writing down. There's actually a physical or a learning connection to be made when you're writing down information. But here let's start with some conventions. V sub m, and it may not be so explicitly labeled, but that's the maximum amplitude of these sinusoidal voltages, and I sub m. V sub m cosine omega t plus theta sub v. The phase shift of the voltage is then labeled theta sub v. Similarly for the current, it has a maximum magnitude, and then it has a phase shift of theta sub I. But if we wanted, and when we're dealing with power, a lot of times we do want to express our phasors in terms of RMS units, and the RMS quantities are related to the maximum values by this factor of the square root of 2. That's true for sinusoids. If you had some other periodic waveform, then the root mean squared correlation or connection may be a different factor than the square root of 2. But if we're dealing with sinusoids, then the maximum and the RMS magnitudes or values are related by a square root of 2, where the maximum is a square root of 2 bigger than the RMS values. If you need the RMS to compute some powers and you're given a formula and nobody tells you what that amplitude is, you should probably say, I'm assuming this amplitude is the maximum value, and then find the RMS by dividing by the square root of 2. What we will do in this discussion right now is to really just slide the time axis such that we can make the current sinusoidal expression not have a phase shift. So we're really effectively subtracting theta sub I from both of those arguments in our voltage and current waveform. In other words, the voltage now, just to make things a little bit cleaner, the voltage will contain the difference between our phase shifts, theta sub v minus theta sub I, and the current will just be cosine of omega t. That'll just make our analysis a little cleaner or a little more straightforward as we move through the discussion or the derivation that is now about ready to start. So here are expressions for the voltage and the current of a generic element. We're assuming the passive sign convention, and now let's just compute the instantaneous power from these expressions. What's the formula for the instantaneous power? Okay, P is equal to IV or VI, and that's a function of time. P of t is now V of t, I of t. And using these expressions that I now have agreed that we're going to use in this discussion, then we could write that as equaling V max I max, pulling all of the coefficients out front, cosine omega t plus theta v minus theta sub I times the cosine of omega t. And to simplify this, we're going to start using a lot of trig identities or trig relationships. Now we have a product of two cosines. Pretty soon we'll have to worry about the cosine of the sum of two angles, or the difference of angles. If I now call this argument alpha and this argument beta, then we can actually, using some trig relationships, let me just say, here's what I'm now going to use. A trig identity that's coming to us from Appendix F in your book. And it's related to the product of two cosines. And here's where I'm now saying, oh, there's alpha and there's beta. This is now equal to 1/2 cosine of alpha minus beta plus 1/2 cosine of alpha plus beta. And you maybe didn't use this strategy in high school when you were in trig, but we can verify this using Euler's relationship, or the fact that if we wanted to, we could write cosine of x as a combination of complex exponentials. Cosine of x is just e to the jx plus e to the minus jx, all divided by 2. If you wanted to verify this trigonometric identity, you could use this Euler relationship to verify that. But we're simply going to use cosine alpha times cosine beta to try to get some better understanding of what this instantaneous power expression looks like. It's now VI times these two cosine terms, and that now says that P of t is going to equal 1/2, and that 1/2 is coming in from this trig identity, VMIM, and the first term is going to be alpha minus beta, which is going to then eliminate the omega t in the argument. If we now take alpha and subtract beta, we're just left with theta sub v minus theta sub I. So in this first term, we're going to have theta sub v minus theta sub I. And then we have another term, plus 1/2, which is alpha plus beta in the argument of the cosine. This is now v sub m, I sub m, cosine. Now we're adding alpha and beta, so we have omega t plus omega t, or we have 2 omega t plus theta sub v minus theta sub I. And now we're going to apply another trig identity. This cosine of theta sub v minus theta sub I, theta sub v and theta sub I are fixed angles. We now just take the cosine of an angle. That's a number. This first term in the P of t, the instantaneous power formula, is just a constant. The second one is the messy one. It's now shaking or oscillating at twice the frequency of the underlying voltage and current waveforms. It's now going at 2 omega t. But we can maybe help our analysis a little bit if we now think of this as alpha 1 and this as beta 1, and use another trig identity, which is the cosine of alpha 1 plus beta 1. So that now what we want to do is trig identity number 2 is to say, oh, the cosine of alpha 1 plus beta 1 is now the cosine of alpha 1 cosine beta 1 minus sine alpha 1 sine beta 1. And we're going to apply this trig identity to the second term in P of t, so that now we end up with 3 terms in our expansion or in our formula for P of t. The first term just comes through. We haven't changed that, but now what we're trying to do is isolate some of this time-varying behavior in our formula for P of t. And maybe with that cosine of 2 omega t plus an offset, you're going, that's kind of a mess. So let's clean it up by using this second trig relationship to obtain P of t is now the first term, Vm Im over 2 cosine theta sub v minus theta sub I plus, and now we have 2 more terms. So let me say plus the first piece, which is 1/2 Vm Im. This is now cosine theta sub v minus theta sub I times the cosine of 2 omega t. And then we're going to account for that negative sign in this trig identity. And now we have a minus 1/2 V max I max sine theta sub v minus theta sub I sine of 2 omega t. That's now our instantaneous power. And if we needed to, we could sketch that if we wanted to. But one way to make this maybe a little cleaner is to realize, what do we know about that particular argument? It's constant, isn't it? So the cosine of an angle is just a constant. This whole piece right here is a constant times a constant, Vm Im over 2. So that first term in this 3-term expansion for P of t is just a number connected to Vmax, Imax, and the phase angles, or the difference of the phase of the voltage expression and the current expression. We also know that this and this will just be a number, and then the second and third terms in this expansion are just some scaled version of a cosine 2 omega t and a sine 2 omega t. So those are shaking twice as fast. The instantaneous power is shaking twice as fast as the original voltage and current. And coming out of the wall, what's it shaking at? In the US, it's 60 hertz, which is 2 pi 60, or roughly 377 radians per second. This power, the instantaneous power, is shaking twice that fast. It's now at 120 hertz, or 377 times 2. That's the instantaneous power. In a generic element that has a cosine waveform that's shifted in phase different from the current by this angle, theta sub v minus theta sub I. That's going to be kind of tedious to keep track of. Sketch the instantaneous power of all 3 of those generic elements in your circuit. Probably wouldn't give you that much insight anyway to sketch it. It might take you a while. That's why you have the full 75 minutes for each exam. But this is just the beginning of one problem. and your exam might have 40 problems on it or something. I can sign drop slips at the end of class, so don't everyone come up right now for that. And hopefully you'll learn that some of the things I say are not necessarily true. Okay? So, if this is going to be tedious to keep track of, this is now a cosine and a sine. Those are kind of nice behaviors in terms of their time history. If I now integrated those or averaged those, the highs and the lows are going to average out. And if I now average these over a period, the last two terms are going to go away. So if I wanted to know, well, okay, this is shaking violently at twice the normal frequency, and I have a cosine and a sine, I don't care about that instantly. On average, what am I doing? What am I having happen? Well, we can average the instantaneous power to find the average power of that generic element or any generic system. And if we do that, that will give us then our real power. The average power, or I may refer to that as the real power. Do you see what, if I now average this, and this is why you spent, whoops, go away. I'm not shopping. Oh, now I am. We'll see what I want to buy today, but this is now 1 over t integral of p of t dt over one period, 0 to t. And what's that going to produce? If I now integrate this p of t over one period of time, and what's the period? How is the period t related to the frequency that I was just talking about? Okay, it's 1 over the frequency in hertz. That's the t. So in this case, if we wanted to know t, we know that omega is 2 pi f, and f and t are reciprocals, so I could now use this expression or relationship to find the period t. Somebody was actually calling in for that answer. I don't know if anyone else heard that or not, but they got it right. But what happens to these cosine of 2 omega t and sine 2 omega t if we integrate them over one period of the original signal's frequency? We have two periods of oscillation with the same amount of positive and negative area under the integral. Those disappear. And we are left then, since these, let me just write that, cosine of 2 omega t and sine of 2 omega t, those terms actually integrate to 0. And our p average now is just going to equal that first term averaged over one period. But that first term was a constant. And if you now average a constant over one period, you get that constant back. P average then, capital P average, is now going to be 1/2 V max I max cosine theta sub v minus theta sub I. And what we will start to learn, well, what we do know is the relationship between RMS values and maximum values. V max is the square root of 2 V RMS, and I max is square root of 2 I RMS. If we plug in RMS values for these amplitudes, we see that P average, another way of writing it, is really just going to be VRMS, IRMS, cosine theta sub V minus theta sub I. And there we don't have to worry about this scaling of 1/2. We just say VI cosine theta V minus theta I. That's the average real power. And the real power, one way that you could think of that, which is the average power, this really is measuring the rate of energy consumption let's say used to transform from, let's assume, an electrical energy to another energy. If you're trying to now power your air conditioner, you're now turning compressors, fans, etc. That was being supplied by something electrical. You're now consuming that electric, or what's the average power. That's what we're measuring. That's what the power company is interested in, or that's what you're paying for in this context. Now that we have that established, this connection between instantaneous power and average power, let's look at some impedance values. And when you were learning to walk, did you start out sprinting? Yes, you did? To stay balanced? Okay, well, who knows? I probably stumbled. But you usually start slow, correct? Let's start slow by just saying, let's look at a simple impedance where the impedance is just a number, a real value, a resistor. And try to understand what's going on here. If I now looked at a resistor, what's the relationship between the current and the voltage associated with a resistor? If I looked at the signal, or the waveform, voltage waveform and the current waveform of a resistor, what can you tell me about those two time domain waveforms?
Is it that they're the same? Like they're not in phase from one another?
So the current and the voltage with this resistor, this is the resistor, the current and voltage, how are they related? By Ohm's law, right? So now V is equal to Ri, and R is nothing magical about that. That's a constant, so the V and the I are aligned. They're in phase with a pure resistor. With this resistor, then, the current and voltage are in phase. That's what we mean by being in phase. Their peaks and troughs are aligned. That says, then, that theta sub V and theta sub I, the phase shifts, are actually the same. So theta sub V and theta sub I are the same for a resistor. And what does that now say about the average power? Using RMS units on our voltage and current. Now we can go back here to our average power expression and plug in the fact that theta sub V is the same as theta sub I. Cosine of 0 is 1. The average power associated with a resistor, you tell me it's RMS voltage, you tell me it's RMS current, I can give you the average power of that resistor. It's just VI. And that will have the units of watts. That was the crawling aspect of this discussion. Let's now move to the next stage and worry about Eli the Iceman. Did we talk about that last time or not? I'm getting a chuckle. Maybe Dr. Marcelin talked about Eli the Iceman. Very briefly? Well, you should remember Eli the Iceman until you retire. No matter how many times people tell you, you better remember it until you retire. And what does Eli the Iceman provide us with? It basically is a mnemonic way of remembering Ohm's law for inductors and capacitors. That's how I like to think of it. Meaning, here E is the electromotive force, so that's the voltage. The voltage of our inductor. This Eli, these three-letter acronyms, give us something, a component, and something. And the first something is what it's equal to. The second one is the scaling parameter, inductor value or capacitor value. And the last variable is differentiated with respect to time. Meaning, the voltage-current relationship of an inductor, because we can write down Eli, now we can just write down V is equal to L di sub L of t dt. That's what Eli tells us. Similarly for ice. So now let me kind of draw a line down the center of my page and say that now I have the current is equal to C times the time rate of change of the voltage across that capacitor. And that is the center variable in Eli and ice respectively. V is equal to L di dt. So if somebody says, oh, what's the current voltage relationship of an inductor? You can go, oh, gosh, Eli. Write down Eli and now you have it. V is equal to L di dt. Capacitor, ice. I is equal to C dV dt. Now you know the current voltage relationship, Ohm's law, this generalized Ohm's law for an inductor and a capacitor. Ohm's law for a resistor, V is equal to Ri. Uri. He doesn't like ice or Eli, but that's the resistor. I don't know where that came from, but ERI, that's a singing group, isn't it? You guys don't know what I'm talking about, do you? I don't either. But I'm just saying that for a resistor, Ohm's law would be ERI. But it's not because you're not differentiating, right? It's just V is equal to Ri. It's Ohm's law. Yeah, whatever. So, what can we say about this particular expression from Eli? Well, we can see that I is actually after or following the voltage, and that tells us something too. So we can tell more from Eli than just V is equal to L di dt. We can say, oh, I is actually following or after the voltage. So let's write that down. We can say that the current in Eli what did I just say? Current comes after voltage. Is that what I said? Who knows? Wake me up. I'll just play this back at some particular time. At 35 minutes in and double check. I'm not going to do that, but you can. Current comes after the voltage. If I said it wrong, this is what I was trying to say. In terms of this expression for Eli, the current comes after the voltage. For ice, what's the current do? The current comes before the voltage in that three-letter acronym. Which means then, now if we just say that, we can say, oh, the current lags the voltage in an inductor L, and the current leads the voltage in a capacitor. So if you're struggling with what's leading and lagging, go back to Eli the Iceman, and that will help you, give you a way to remember that current lags the voltage in an inductor and current leads the voltage in a capacitor. That's now on our cheat sheet. We've written that down. Now we can go and step a little bit further into these impedance relationships relative to average power. So let's now look at an impedance of an inductor. What's the formula for the impedance of an inductor from chapter 9? J omega L. So that's the impedance of an inductor, or we might actually just collect omega and L into one factor and call it Jx sub L. So that now we have this inductor impedance. What's the average value here? Well, let's follow what we know. We know that the current lags the voltage, and we know that the generalization of Ohm's law would look something like that. V is equal to Zi. That's the generalized form of Ohm's law, and now I've written bars over those to indicate that they are phasors or complex quantities, the voltage and the and the current, because I'm assuming we have sinusoidal variation in our system. And now let me just expand or be a little bit more specific on what this phasor form of V and I look like. Let me say that V sub L is now V sub RMS. That's just a number. That's the magnitude of this phasor at an angle of theta sub V. Z sub L, we just said, was J omega L. And I sub L as a phasor, let me write that as I RMS at an angle of theta sub I. And we can actually write this in a form that makes it maybe a little more intuitive as to how we can combine these angles and magnitudes. J omega L. Can I write that as a complex exponential? J is really just going to be orthogonal to the real axis, correct? So now think of the complex plane, the real line being horizontal, and the imaginary component of the complex plane is vertical, and that's in the J direction. So J omega L is something straight up in the vertical direction of the complex plane, or we could write this as omega L at 90 degrees. And we could write all of these phasors in terms of complex exponentials. We could now say that V RMS e to the j theta sub v. That's the same thing as saying at an angle of theta sub v. V sub m, that's the magnitude, e to the j theta sub v. That's the Euler form of this angle, theta sub v. That angle theta sub v, if you wanted to put that in rectangular form, would be Vm cosine theta v plus j sine theta v, and that's really what e to the j theta sub v collapses into or represents. So that now if we have omega sub L at an angle of 90 degrees, we could write this as omega L e to the j 90 degrees. And the current is I RMS j theta sub I. All I'm saying really, if you're trying to figure out what's going on, here's the real axis, here's the imaginary axis, this is a complex plane. And if somebody now wanted to know where is J, he's next to Bill. No, this is J being the complex. You have to be awake to stay up in this lecture. There's J. It's now at this angle of 90 degrees. It's orthogonal to the real line, and it has a value of 1. That length of J is 1 in the 90 degrees direction from the real axis. If that's now the case, this relationship is the relationship of a pure inductor's voltage and current. And what does that tell us if we say, oh, let's look at the phase of the voltage relative to the current in our inductor? If I now said, well, what's the phase look like? Then I just need to look at the arguments in these complex exponentials. I can compare them. Theta sub v on the left is equal to the combination of those phasors on the right. And I now have e to the j 90 times e to the j theta sub I. That product is just the sum. Or now I can say that theta sub v, the angle of my voltage, is 90 degrees plus theta sub I. Or I can now say that theta sub v minus theta sub I, subtracting theta sub I from both sides, is 90 degrees. And that's really what I was looking for, because I'm trying to find the average power associated with a pure inductor. P average is then V RMS of that inductor. What's the RMS voltage associated with that inductor? What's its current? Well, that's I RMS cosine of theta sub V minus theta sub I. But that's just cosine of 90. And that says then that the average real power associated with a pure inductor is 0. There's no real power associated with a pure inductor. And now you're probably going, well, something's lost here. I've got a lost puppy or something. Yes?
the average power supposed to be V max I max?
So now it depends. So the question was, I thought the average power was V max, or it depends on which formula you're using. We have these two. So if we think of the average power in terms of maximum values, it's 1/2 V max I max cosine theta V minus theta I. And now we can see that the average power in any element depends on this relationship of our voltage phasors, our voltage waveform's angle or phase, and the current waveform's phase. For a resistor, we learned that theta sub V was the cosine waveform was in line with the current waveform, so theta sub V equals theta sub I. We have cosine of 0. And then we had an average power for a resistor was just VI in RMS units. We now have learned for an inductor the relationship between the voltage phasor and the current phasor. Those two waveforms differ by 90 degrees. What's the cosine of 90 degrees? That's 0. Now we are seeing that the average power, this is the power absorbed or taken out of the system by an inductor. It's not taking anything out. Is it true? What? You're questioning that fact? I'm finished. I'm done. I am almost done by this clock, but I'm not really. So what did we learn? Now we have to scratch our head and say, what in the world is going on? I'm not sure I answered the question, but now it depends. The average power depends on the impedance. If it's a pure resistor, then it's VRMS, IRMS. If it's a pure inductor, no resistive components of that inductor, it's an ideal inductor, we have 0 real power, average power. So now I was trying to be a little bit cute and say, where did that current go? Like we had a lost puppy or something. Now we have a lost current. What? We have voltages and currents going up and down, and we have 0 real power. What's going on? Where does the current go? If we have a pure inductor. Well, let's go back. So now we go back to the instantaneous power. We derive that generically, so we can use whatever elements we want, and here we have an inductor. So here we can say, well, this is 1/2 V max I max cosine of 90 degrees for that inductor. So that term goes away, and that's our average power term. But we also have plus 1/2 V max I max cosine of 90 degrees cosine of 2 omega t. That one goes away too, because cosine of 90 is 0, and that's one of our coefficients of the second term. We maybe have really lost this current. But now let's look at the third term. Minus 1/2 V max I max sine of 90 degrees sine of 2 omega t. What's cosine of 90? I'm 0. What's sine of 90? 1. So now we do have instantaneous power of that inductor. And what is it? Well, P sub L of t is now equal to minus 1/2 V max I max sine of 2 omega t. Let's write that down. Wow, the instantaneous power is twice the frequency of the frequency of the current and the voltage. And what else can we say? Well, the instantaneous power, P sub L of t, in this inductor oscillates. It's going as a sine of 2 omega t. The instantaneous power is just going back and forth, back and forth, back and forth. So, what we can say is that when this instantaneous power, when P sub L of t is, let's just think of two different things. What if it's positive? What if, because half the time it's positive, because we have this sine waveform at twice the frequency of 60 hertz. When it's positive, what's happening? Well, now this inductor is actually storing that energy in the magnetic field of that inductor. And when it's negative, it's pushing it back to the source. It says, I want it, no I don't. I want it, no I don't. And it just going back and forth, back and forth. How fast? 2 omega. But what's real? What's being transferred to convert from electrical to anything else? Nothing. This guy, you're just enlarging the magnetic field, collapsing it. Enlarging, collapsing. And nothing's really being done work-wise with that energy. You're just building up and letting it go. Building up, letting it go. So it's like you're blowing up a balloon, deflating it. Blowing it up, deflating it. It's just giving and taking. No net take, no net give for that inductor. So the energy is stored in the magnetic field when it's positive. And when it's negative, the energy is delivered back to the source. Now the power company is not going to like that. Because what? That current is running up and down those transmission lines. It's just going boom, boom, boom. So if we had zero impedance on that transmission line, no harm, no foul. But it's more difficult for the power company to generate this reactive power, even though you're not receiving anything. You're sitting over here, well, that inductor's not doing anything for me. But the power company is having to give you more energy to power your machines because of that. So now the power company would like to keep track of that. So we would like to keep track of this energy that's going back and forth due to this ideal inductor in our system. Since the current is actually flowing in the transmission lines. Now we can't keep track of it by measuring the real power, can we? Because we'll find that that's zero. But we can measure something that's orthogonal to the real, and that's the reactive power. And how do we, the real power was cosine, orthogonal to that is sine. So the way that we will keep track of this is to define a new term called the reactive power. And since we've already used P for power, we'll call this Q. And this is now going to be an expression that's orthogonal to the real power. So now we're interested in the sign of theta sub v minus theta sub I. And a lot of times we will simply say for a generic element, oh, what's the angle of that impedance? And then we'll have a reactive piece and maybe a real piece, because that angle may not be 0 or 90. It may be somewhere between, so it's going to have a component that's real and a component that's vertical or reactive. And we won't call this watts. It's volts, it's amps, and it's reactive. So we'll just call it VARs. Volt amperes reactive. This now has units of VARs. And we might as well introduce some new terms to keep track of that. You can see that these two formulas both involve V and I, the real power and the reactive power, so that's the same, but they differ in that cosine of the angle and the sine of the angle. We'll call the sine of that angle difference the reactive factor. That's the sine of theta sub v minus theta sub I, and we might abbreviate that as lowercase rf. And the power factor is cosine theta sub v minus theta sub I, and we'll call that lowercase pf. Or in terms of this average power expression, this is now V RMS I RMS cosine theta sub v minus theta sub I. Now we can see that the power factor is the same as the cosine of the angle between the voltage and the current. And if we had measurements of the power, the real power, and the voltage and current in RMS value, we can now find the power factor. And if we had a purely resistive load, then this power factor would be what? 1. So the power company would treat you nicely if you have a power factor of 1, because you're not asking for this reactive power. If the power factor starts getting less than 1 by a significant amount, the power company will start charging you more for the power that you're actually using. Question?
So is reactive power sort of like, I don't know if it's right to say this, but like the imaginary?
So the reactive power is the imaginary component of our, what we will call our complex power. We have a real power, we have a reactive power. They are orthogonal. Now we're just going to start drawing triangles. We can have a real part and an imaginary part, and we can connect that with a hypotenuse, and that hypotenuse represents the complex power. So the reactive power is the imaginary component of the complex power. So you could think of it as the imaginary piece of this complex power, the reactive piece. Okay? And this particular product, VI, that's the apparent power. We have all these different powers floating around. That's why I had power in quotes at the beginning of the class. But this now, we have a word for this. This is the apparent power. Now, if we don't have a pure inductor, but we have a circuit that has some resistance and some inductance, no capacitance, then we have more of an inductive circuit. That means then if we have an inductive circuit, it's not purely resistive, it's not purely inductive, it's a combination. Then what do we know about the current relative to the voltage in that circuit? What's the relationship? And here you have one of two options, lead or lag. So now you could flip a coin and you have 50% chance of getting it right with a lead or a lag answer. The current does what relative to the voltage in an inductive circuit? So take it to the extreme. What's the inductor do? Lag. We have an inductive circuit, so the current maybe isn't 90 degrees away, but it's a positive angle. So now the current lags the voltage in an inductive circuit. That means that theta sub v minus theta sub I, which we maybe have called theta, what's that value? It's positive now if theta sub v is bigger than theta sub I. That's kind of what current lags voltage means. So this is now bigger than 0. And if we go back to our Q formula, which was VI sine of a positive angle, what's the value of Q? Sine-wise. It's positive. So now we know our reactive power when we have an inductive load, Q is positive. And we have what's called a lagging power factor. Because if we take the cosine of an angle, cosine is even. We have to tell each other a little bit more information than just the cosine of a number or an angle, because we're going to lose whether it's leading or lagging, since cosine is even. So we have to now know that if we have an inductive circuit, we have a lagging power factor, in addition to the value of that power factor. It might be 0.8, and then we would have to say, oh, it's 0.8 lagging. You would have to give us a little bit more information, because once somebody takes the cosine of an angle, whether that angle is positive or negative, you're going to get some positive number. Let's say if our angle is between plus and minus 90. That's the information for an inductive circuit. We can do the same development for a capacitor, a pure capacitor. What's the impedance of a capacitor? That's 1 over j omega c, or if we multiply by 1, j over j, j squared is minus 1, and so now we have minus j times 1 over omega c, or this is now minus j x sub c. And this is our impedance associated with a capacitor. And we can now say ice, where the current leads the voltage because of this mnemonic. We have the generalized Ohm's law formula, V is equal to Zi. We can plug all of that information in, and what are we going to find for the phase? If we did the same kind of analysis that we did before, theta sub V is now that's minus j, so now we've gone downstairs relative to the horizontal line real axis in the complex plane. This is now minus 90 degrees plus theta sub I, or subtracting theta sub I from both sides, we now have the difference between our voltage phasor and our current phasor is now minus 90 degrees. So if we now wanted to find the average power due to a capacitor, an ideal capacitor, this is now VRMS IRMS cosine of minus 90 degrees. We're back to 0 watts. And we would expect, if we went and looked at or examined the instantaneous power of a capacitor, P sub C of t oscillates, and in this case, when P sub C of t is positive, what's happening? Now that energy is stored in the electric field of that capacitor, and when it's negative, it's giving that energy back to the source. So it's, again, oscillating at twice the frequency, but now we're charging that capacitor and discharging, charging, discharging. And it's an ideal capacitor, so there's no resistive losses in that capacitor. So when P sub C of t, the instantaneous power of our capacitor, is positive, we have energy being stored in the electric field. And when it's negative, energy is delivered back to the source. And now if we said, oh, I actually have a net capacitive circuit, what can you tell me about the relationship between the current and the voltage of a capacitive circuit? Go back to ice and just say, oh, ice. I leads voltage. So I have a circuit that's more capacitive than inductive. It's now a capacitive type circuit. My current then leads the voltage. I can then look at this relationship of the voltage and the current, their phasors for a capacitive circuit. If that's now theta, what do I know if current is bigger than, if the current phasor or the angle of the current, theta sub I, is bigger than theta sub V, what's theta? Sign-wise, it's negative. So that now, what's Q? Sine of a negative angle, that's negative. And we would say that this now has a leading power factor. We're going to have what? A lot of different impedances making up our full circuit. Some inductors, some capacitors, some resistances. So in general, we're going to end up with something more difficult or more involved than just a pure resistor or a pure inductor or a pure capacitor, which means we're going to have complex impedances. to deal with. If we have complex impedances, then what do we know about the power? We're going to have a real part and a reactive part, right? We're going to have two components and they're orthogonal to each other. We now have then, if we have complex impedances, we now have complex power. And that complex power is P plus an orthogonal component, which is Q, and we are now going to call that S. So the complex power, when I just say complex power, that's S. This is now a complex number. Sometimes I'll bar it, sometimes I won't, but this is now a complex number. P, what do we call that? This is our average power, or the real power. Q, that's our reactive power. And if we put all of this together, we have the formulas for P and Q. S is now V RMS, I RMS, cosine theta sub V minus theta sub I, plus, that's the P, plus the JQ, but I can write that, going back to Euler. Euler's your friend. Euler says that cosine x plus j sine x is e to the jx. That's the relationship that Euler gives us. We can use that here to our advantage. We can now say, oh, I can write that a little bit more compactly. I can say V times I. That's common to both of the terms. But I have cosine plus j sine of the same angle. And that's just e to the j of that angle. So this is now e to the j theta sub v minus theta sub I. And now we can pull this thing apart, or distribute that e to the j. We can break it up into two products, or a product of two terms. Since we're subtracting exponents, we can simply make the product, or we can now say, oh, this is V RMS e to the j theta sub v, and it's I RMS e to the minus j theta sub I. What are those? Complex numbers. That's just a phasor representation of our voltage phasor. Here's our current phasor, but it's not quite our current phasor because of that negative sign in the exponent. But we can find that by taking the complex conjugate of our current phasor. So this now, this we said was the complex power S. S is now V RMS as a complex number. I RMS as the conjugate of the current phasor, and this has units of volt amperes. Where this ugly thing, you can make yours a lot cuter or a lot better. That's the complex conjugate. But that's VI star, and you wondered where that came from. Now you give me the voltage phasor and the current phasor of any complex interconnected system, and I can tell you its complex power. I just take the voltage phasor times the complex conjugate of the current phasor, and I have the complex power. And what's that going to give you? That's now going to give you the complex power, which in fact we can now maybe think of that geometrically as a triangle. We can now say, oh, I have a real part, there's P. I have an imaginary part, there's Q, and now I have the hypotenuse, which is S. And what's this angle? And what's this particular picture of? An inductive load or a capacitive load? Still writing. What's that angle? Positive. Q is positive. It's inductive, isn't it? So this particular complex power triangle is illustrating the fact that Q is positive, or we have an inductive load. And from that triangle, you can find the real power, you can find the reactive power, you could find the apparent power, which is the magnitude of the hypotenuse. We can find the complex power, we can find the reactive factor, we can find the power factor, it's lagging. We found that current. You know, we thought that current was lost. We've got it now. We'll pick up here next time.